Okay, 15 seconds. Okay. Thank you very much all for joining our new webinar in accordion. Today I have the pleasure to introduce Fulvio Risso, that went from Risso of Torino, and he will explain us his new line of research, that is the liquid computing. I think it's a pleasure to have here, and let's see how we will move on edge cloud continuum computing. Fulvio, the floor is yours.
Thank you very much, Ferran. I'm sharing my screen. Okay, perfect. So, good afternoon, everybody. Thanks for inviting me to this seminar. So I would like to introduce our idea of liquid computing, that, by the way, is yet another term that we have to invent in order to create some noise. But, you know, other people are talking about computer continuum and so on. So, okay, that's really the space. But what we did, probably, that is a little bit different from other groups, is that we created a real software that works. Obviously, it's not perfect, but it works, and it is already being used in production in some environments. So I would like to introduce how this idea works, the motivation, and so on. So first, let's start with a big disclaimer. So we're talking about cloud. Actually, we are talking about Kubernetes. I know that Kubernetes is not cloud, but if you want to do something that really works, you have to select your space. And our space is Kubernetes for different reasons. I feel it's a wonderful technology and so on, but just to make sure that we are supporting only this system. And the second point is that we're assisting in Kubernetes to a big problem, which is called the cluster sprawl. That means you have so many clusters around. So what is a cluster? Okay, a cluster is a cluster in the cloud, like in Amazon and so on, but it can be also a device with a small version of Kubernetes like K3s and so on. So in general, you have a lot of objects that can be considered clusters. And there are a lot of reasons for that. I don't want to go this. The point, though, is that when you have a multiple cluster, whatever cluster is, actually, it can be even a single device acting as a small Kubernetes entity. You have this kind of rigid silo approach. What does it mean, rigid silo? It means that if you have an application and that application is made by multiple microservices, in this example, we have 3 applications, the green, the red, and the yellow. When you deploy an application, you have to select a given cluster, and then that's it. It runs in the cluster. Be careful, I'm not saying that we cannot create multi-cluster services. Of course, I can take maybe 2 components here and deploy into another cluster. This is absolutely feasible. So right now, we can use multiple clusters, definitely. The problem is that this approach is not transparent. So when I deploy an application that has to use multiple clusters, I have to tell the app, you have to go 2 pieces in this cluster, 3 pieces in the other. And if something happens, this is not transparent. So the way one component talks to the other is different whether they are in the same cluster or in a different cluster. And this is basically the key point of our approach and the key problem that we want to address. So we want to take those rigid silos and create something that is borderless. So when you have your apps, you can deploy your apps in, let's say, in the continuum, but in the same way as the app was deployed in a single cluster. So for us, transparency is completely the key value here. So we do want deploy an app in multiple clusters as they were a single cluster. And this is what we aim to do with this liquid computing, so this LICO project. Of course, this is not the end of the story because, you know, when you want to deploy things in multiple clusters, okay, maybe you want to also control a little bit because, you know, maybe it's better to keep your data in a specific countries, or better, it's better to have maybe one instance of a given service per country for whatever reason, or maybe you have another constraints that this service has to run close to customer. Obviously, this has to be supported. And what we envision is the creation of policies that within this continuum allows to control, if needed, where your services are located. So currently, LICO does this kind of borderless orchestration, and some initial support for policies is already there, but you know, it's an ongoing process, so we still have some more work to do here. So how do we create this virtual continuum? So the idea here, the keyword is the concept of virtual cluster. Let's take this example. We have 8 clusters, absolutely traditional clusters. What we do is that we create a sort of aggregation. The aggregation is made by putting together an arbitrary number of clusters, so there is no limit here, and selecting one cluster as the entry point of the aggregation. Entry point means that if there is a human, like a person that is deploying services and so on, has to deploy the services here on the one that has been selected as the entry point. I don't want to call it master because there is no master, there is no slave, there is definitely no concept of more important or less important or master or slave. No, all the clusters are equal. There is only the concept of the entry point. So when you deploy a service here, actually the service can be deployed on any place in the continuum. The number of clusters, virtual cluster, is arbitrary. So that's another cluster, the green cluster, and this is yet another, the yellow cluster. It's interesting, though, the yellow cluster, because the yellow and the red cluster are both using some resources of this gray cluster on top of the picture. Because, you know, when a cluster, physical cluster like this one in the picture joins a virtual cluster, has the right to tell how many resources have to be dedicated to that cluster. So maybe I can say 50% of the resources are for me, 20% are for the red cluster, and 30% are for the yellow cluster. Okay, this is absolutely one of the things that we can do. So, if you own a cluster, you're still an owner of the cluster. You're still in control of the cluster. So you give some resources to other virtual cluster, but it's everything under your control. You decide. So what can we do with this virtual continuum? So with this virtual cluster? Okay, there are a few examples here, and then you can envision other. A first example is cloud bursting. This is the example that we are running in production in our university. We have a cluster, has limited resources, and when the exams come, we need more resources in order to support thousands of students doing the exam exactly at the same time, which is usually not needed during the other time of the years. So we borrow resources from another cluster that we have in university. We create this virtual cluster that allows us to absorb this burst of demand that we have during February and July. Another example is cluster migration. This is something that many people are concerned of because they need to have a cluster, they need to maybe upgrade or migrate the workload to another cluster for whatever reason. Okay, LICO is not perfect for that, but can have this kind of migration procedure. Or private data spaces. Data spaces are something that are very well considered and studied right now in Europe. You can see in Gaia X organization, there is a part of the group that is working on data spaces. Okay, we can do similar things. We got a project funded by Giant in order to investigate those kind of private spaces done at the infrastructure level instead of done at the application level. Another use case is multi-cluster orchestration for cost optimization. So we have like an entry point here that is, let's say, just a control cluster that takes into consideration other cluster, let's say at the below level, so like a hierarchy. So they create a sort of virtual continuum, and this is especially useful when you have many clusters at the edge, and you can control all of them through a single cluster or a few clusters at the upper layer. This is another use case that we are working with a company, actually. Or there is a final scenario that you can envision. We're working with Internet Exchange in Italy, in Torino. They are prototyping a sort of broker. So they have multiple clusters offering resources and services. Those are advertised to, let's say, a central cluster, let's say a broker actually, and then are given to customers that are willing to buy. So basically the broker is actually doing this kind of brokering services, selecting the best resources for you and and giving only what you need with the given quality of service and so on. Again, this is research, but it's an interesting approach that we can enable with this kind of liquid computing. So why LICO? Because it's multi-cloud. We support many cloud providers, also public cloud providers, because it's European, and given the current situation across the world, we have to care also of being European, because it allows to reduce the lock-in from hyperscalers, because it's open source, completely open source, and we're targeting a better open governance, because this project was driven mainly by university, but we would like to incubate this project into CNCF. So basically open also to other contributors and having also a governance open, not just the source. Okay, so our objective actually is to provide a common ground for the upcoming European cloud infrastructure. But there is a slide later here. So how does it work, LICO? First, let's see the workflow. The first workflow starts with discovering. So which clusters are available? So in case of cloud, you have to tell the cluster, okay, there is a cluster in the cloud in Amazon with this IP address and so on. But for instance, at the edge, when we're considering the continuum of devices at the edge, we have also an auto-discovery phase. So all the devices that are nearby are immediately discoverable without doing anything manually. Once you know which cluster you can leverage, okay, cluster can advertise resources and services. What is a resource? Of course, a CPU, a memory, a GPU, all those are resources. What are services? Services are basically like a database as a service. So, you know, you can also advertise services, not just physical resources. This is something not supported right now, but it's something that is coming in LICO as well. Once you advertise or what you want to export, it's important here, not everything you have, only what you want to advertise. So the advertisement process is completely under your control. Then, if the other cluster agrees on or it likes what you are advertising, yeah, it can peer to you. You know, this word peering has not been chosen just another word, but peer means really we are peering. There is no master, as I said before. We're just two clusters that are sharing resources and services and information. And then at that point, you can use all the resources. And once this is done, you can de-peer. The peering and the de-peering process is very fast. It's on the order of 2 seconds right now. So it's very, very fast because our aim is to enable peering and unpeering in a very fast condition, even to leverage other resources for a little amount of time. So when you peer, is not something that you have to do for days or months. You can even peer for a few minutes because the cost of the peering is very, very small. So we aim at a very dynamic system. Which are the main ingredients in LICO? So basically you have 4 main ingredients. The first is the network and storage fabric. So we have 2 clusters here, the first cluster and the second cluster, and they are joined into this continuum, which means that if you have a pod like A running here and another pod like B running on the other side, they don't need to see any difference depending on the location. So A thinks B is local, while it is not. But everything A could do with B, if it was local, has to be done also with B that is on the other side. This is what we call fabric, because there is a sort of fabric underneath that guarantees all the network communication between all resources, pods, and so on into Kubernetes, like they were absolutely local. And the same for the storage. The storage can be on the first cluster, on the second cluster, it doesn't matter. It's completely transparent to you. So those components that we call network and storage fabric is complemented with what we call service fabric. The service fabric is what works at the Kubernetes level. That means Kubernetes here thinks all the resources are local. So even B, C, and D, even if they are actually running on the other side, but the control plane of Kubernetes thinks everything is local. There is another slide that explains how this is done. Of course, this is valid also for the other side. So on the other cluster, you can see here A, so the pod that runs on the cluster number 1, that is perceived as local as well. And finally, the last component is the resource reflection component. So let's pretend this B pod is running. So if I ask the first Kubernetes here, what's the status of B? Okay, Kubernetes go here and checks and say the pod is running, but how can it know that the pod is running? Because the resource reflection is actually duplicate relevant information from the target cluster to the local cluster in order to see everything here local with the proper state. So the resource reflection is the component that aligns the status of the resources on both sides. So actually, it propagates back the status of the resource B, but let's imagine like the user decide to interact with the resource B and say, stop this pod. Okay, I have to propagate this kind of order over there in order to stop, in order to create this continuum in a completely transparent way. So I think it's pretty clear that this is the LICO magic. So this is where the LICO comes into play in order to guarantee this complete transparency. So actually, the keyword that we would like to highlight here is dynamicity. The system is completely dynamic in order to create this desired service continuum. We're leveraging quite a lot virtualization, actually cluster virtualization, in order to create a unique, homogeneous virtual space across multiple clusters. So an app, a service running in this virtual cluster doesn't see any difference independently from the actual location of the other components. And finally, ownership. Ownership for us is very important because in the real world, all the cluster may not be under our control. So we may need to leverage clusters that are under the control of other entities, other administrative entities, and each one should be still in control of its own resources. So being still in control of your own resources is very important here. So I'm almost at the end of this first part. So how does it work? So how this kind of reflection and service fabric and blah, blah works. So let's take a cluster. Let's call it the home cluster. Your cluster has some servers, which are called nodes in Kubernetes. So in this case, just one. When you decide to peer with another cluster like these other clusters here, so the peering process actually creates a virtual server in your own cluster. So the idea is that if you had one server before, one node, now you have two nodes. Actually, it's not a physical node. It's a software, it's a virtual node, but is perceived by Kubernetes as a real node. So Kubernetes doesn't see any difference in this respect. So who is more familiar with Kubernetes can see that here is done with the virtual kubelet, a project started by Microsoft several years ago that is exactly doing this. And this virtual node actually virtualizes all the resources that you can find on the remote clusters. Actually, not all the resources available, but all the resources that have been offered to your cluster. So if you have two nodes here, you put all the resources together, like the number of CPU on the first node and the number of CPU on the second, you aggregate and you export them here. So this big node, the name big has not been chosen by chance, but it really highlights that this server, this virtual server, becomes an aggregation of all the resources that you have on the remote cluster. And then you can repeat this process as many times as you want. So you can peer with other clusters and so on. And once you start a service, as we saw in the previous slide, actually the service, the pod, is maybe started on the remote cluster or maybe on this physical node. It depends on Kubernetes, it depends what you prefer, what you choose. But if it is started on the remote node, a shadow copy, so a shadow information, shadow object is created on the virtual node on your home cluster in order to allow you to see actually this information actually like it was local. So what we can do here, actually, there are two ways of using this kind of virtualization. The first is the one that I introduced so far, and this is what we call the elastic cluster model. So you have a cluster with physical nodes, so already servers, and you add some new virtual nodes here, so your cluster becomes bigger. But the same technology can also be used in another model that we call the supercluster model. That is basically more oriented to aggregation. So your home cluster can be actually a virtual cluster without no physical servers. We have only virtual servers there. So it becomes a sort of aggregator of all the resources that you have on the foreign clusters. So I cannot say this is better, this is worse. And by the way, it's also a wrong statement. This is better, this is worse. It's just a matter of which is the model that fits your objective. LICO actually supports them both. And in this case, when you have this kind of hierarchy, you can also think about having multi-level scheduling, because actually when you start a service, the service, actually a pod, is taken by the first scheduler by your home cluster that decide where has to go. And if the pod is scheduled on the virtual node, actually the pod is taken by a second level scheduler, and it goes there on the real cluster where there is another Kubernetes scheduler that decides on the physical node where this service has to be. So, you know, this kind of hierarchy is definitely a help in terms of scalability as well. So I would like to stop here because I would like to give some room for questions. So if you all agree, I will give the floor to Alessandro, who, different from me, is the one who makes things. I'm just talking and talking, and he can show you a demo of the real system in action, and hopefully you can understand better how it works.
Okay, if there is no question about that, I start with the presentation. Let me adjust a bit my screen. Okay, just a moment. Okay, can you see my screen? Can you see?
Yes, no, a little bit bigger, at least for my side.
Just a moment. I don't know why it doesn't resize the. Just a moment. Okay. So let me present you our demo environment. We have, as we can see, two Kubernetes cluster, one on the left and the other one on the right. We have two kind of clusters, so they are running on my virtual machine, but they can be any Kubernetes cluster, also managed Kubernetes cluster from cloud providers. We can see on the top the nodes that are currently present on each cluster. We have a control plane node and a working node at the moment. Both of them are physical nodes. Then we can see the pods that are in the Lico namespace. That is the control plane of Lico that is already installed on both these clusters. Now we will see our demo, and we will peer these clusters that at the moment are completely separated. And then we will deploy an application on our continuous computing, continuous cluster, our virtual cluster. Now, to start, we need to peer this command, these clusters, and to do that, we can use our CLI tool, that is licoctl, and we can ask to licoctl to generate a peer command in the cluster that we need, where we need to share the resources. So we run our command. He provides us an authentication URL that will be used for the first Lico authentication to the remote cluster, and an authentication token that is used to authenticate the remote clusters. Similarly, as you can do with kubeadm to join a new nodes to your cluster. We only need to copy and paste this command to the other cluster, and when we run it, we can see that in a few seconds we have a new pod in our cluster. That is our virtual kubelet pod that creates a new node in our cluster. The Lico virtual node is, you can see that is exactly the same as these other nodes, and we can see it in the nodes list, in fact. Now, every pod, every application that will be scheduled on this node will be executed in the remote cluster. What we can say is that Lico works at namespace level, so we need to enable each namespace that needs to be offloaded. This means that we can control which application are Lico enabled with not, because we can have different policies for different applications. What we can do is to monitor the namespaces. So we get the namespaces in the remote cluster. We see when the Lico namespace, the Lico enabled namespaces will be offloaded. We start with the normal creation of our application. We simply create a standard Kubernetes namespace on that cluster that we call Lycodemo. As we can see, nothing happened on the remote cluster when we create a namespace in our entry point cluster. We need to enable this namespace using, again, our CLI tool, that is, again, lycoctl. We can see to lycoctl to offload the namespace called lycodemo, and using the mapping strategy and foresight name. This means that the namespace lycodemo will also be named lycodemo in the remote cluster. We can run this command, and we can see that immediately a new namespace is spawned on the remote cluster called exactly lycodemo. All the pods that will be scheduled on the virtual node on this namespace will be executed on the lycodemo namespace on the remote cluster. Now we can see which is the application that we will schedule. This is the standard is a demo application from Google. It is an online boutique. We can see the manifest. We only do 2 little changes of this application. We can see in our customize directory. We put node affinity for some of the deployments to ensure that these pods will be scheduled not in the virtual node, so they're executed locally. For some other deployments, we apply the opposite patch, so it's a remote patch. So we scheduled all these deployments on nodes that are virtual nodes. So we are sure that a part of the application is local and another part of the application is remote. This is due to demo purpose to really use our customization, but you can select the topology you prefer using affinities. You can see how we applied this application. Is the standard application developed by Google. We didn't change it. And we can see that some of the deployments are local and some other are remote. It is that. Now we can deploy our application by using kubectl with customize. We can see that we deploy it in the lycodemo namespace. Applying it, some services and some deployments are created on this cluster. We can see that the pods are becoming up and running. We can also see where these pods are running. All these pods, some of them are running on virtual on the worker of cluster one. Cluster one. These pods are running on physical nodes of the cluster, so are running in the local cluster. Some other of them are running on the virtual node. All these pods that we see on the virtual node, we can check that are also available in the remote cluster. Obviously, in the remote cluster, they are running on physical nodes of the remote cluster. We can also check what happens for services. So we can get the services in the lycodemo namespace, and we have the complete list of the services, and we can have the same in the other cluster. As you can notice, the services EPs are different between the two clusters, so each cluster manages it by its own. the load balancer is managed differently on both clusters. We does not have an external EP because we do not have a load balancer provider in these clusters, but it can be different. So you can do external load balancing for your application. We make these services work by reflecting the endpoint slices resources. We can see that for in the remote cluster we have two endpoint slices resources. Endpoint slice is the standard Kubernetes resource that that Kubernetes and kubeproxy use to actually make the services work. So we resolve the service EP with the EP of the remote pod in the case that the pods are remote, obviously. Now we can also check, now that it's all up and running, we can also check that the application is working. Just a moment, I have to forward this port to the virtual machine and get the browser. We can go to that port, and we can see that our application is the Google Online Boutique application is up and running. We can navigate it and use it as it was on a single cluster. And that is, if you have a question, we can go deeper in some details of this demo. Thank you.
I think I can answer to Tarek's question, or because I can add something more technically, but I don't know if this is something that you like, or I will give more space to the discussion now.
No, I didn't read the question, so
okay, no, yeah, but
I missed the question.
Okay. So okay. So okay, let's then add one comment here. So there's the demo. Okay, the status. I will give you the slide to Ferran. Just one more comment. We think that Lico can be an option for a European cloud. So there's clearly a problem here in order to enable, let's say, small, they are actually not small, but definitely smaller than the big hyperscalers, to compete with, you know, the three bigs, Google, Amazon, and Azure. We feel that Lico can be an ingredient for this kind of competition, because the idea would be to transform the infrastructure into a commodity. So, you know, if you have this concept of virtual cluster, in the end, is not that much important where your pods and services are running, because you can see everything into your cluster. So this can also be used to reduce the cost of the switching from a cloud provider to another, because if the infrastructure becomes, let's say, a sort of commodity because you cannot see it anymore, okay, the cost of switching probably will be reduced. What is not clear yet to us is the problem of managed services, but definitely we have to improve the way managed services are created in order to allow also those managed services to be created on other cloud providers, not just on the hyperscaler. So I can start a Kafka as a service, even in Scaleway or whatever, and not just in Amazon. So, you know, this is what we're aiming for. And then, okay, thanks. I can stop my sharing. So let's go to the question from Tarek. which is very interesting indeed. And I would like to say this. Do we have the limitation in terms of the cluster, the entry point? Can it be something like a single point of sorry, failure, a bottleneck, sorry. Definitely, yes. This is definitely something that it could become. Actually, we made an extensive number of tests, and actually, we're not adding significant performance overhead to Kubernetes. This is very important. So if this can be handled by Kubernetes, okay, it's very likely it can be handled by Lico as well. So the overhead we're adding on top of Kubernetes is really small. But definitely, there are some cases in which having a single point of entry may be a problem. On the other side, let's say this. If we make a project super fancy, super scalable, super everything, it will require years and years and years to come into play. So we're already working since 3 years in this project in order to make it, usable. It is used in production. So our feeling was, let's try to do little by little, improve, getting better if it gets attraction and so on. But let's avoid some common problems that we have in Europe that we say, I will resolve all the problems. Yeah, but it requires so much time that it never happens. So I agree with you, correct, but there is also the other part of the answer here. You can use it in production now. Okay, it doesn't do everything, but okay, it does. Okay, I don't know if okay.
About the additional latency incurred because of the multi-level scheduling.
Yeah, multi-level scheduling. Okay, how is the additional latency incurred because of the multi-layer scheduling? Actually, it's the number of schedulers, the number of levels that you have. So the scheduler is still the Kubernetes scheduler. So you have 2 Kubernetes, one on the top and one on the bottom. So actually, the latency in scheduling becomes twice the amount, the original amount. The latency, additional latency introduced by Lico is almost 0 compared to the latency of Kubernetes. Okay, so the more level you have, the more latency, which means Kubernetes scheduling time you get. Okay, which looks fair to me. Okay. Another
question, I think. No, let's make them by order because Tariq Zakaria wanted to make you a couple of questions related to Tariq because we have 2 Tariqs, and then we will go to Emanuele and Lorenzo. If you
yes. Can you hear me?
Yes, sure.
Okay, cool. So I'm working with the other Tariq, by the way, in the same projects, European projects, and we have done a lot of experiments to test the potentialities of Lico. We see it as very good system and tool, as setting up is very easy to set it up. We have some concerns, but let's say these are the points that are interesting that we have found. So, for example, for scheduling, there is something that is built in that Lico can handle out of the box, but you can just specify which cluster you want to schedule to that cluster. And we have some discussions about this multi-level. So we said, okay, when it arrives at that cluster, we can have our own schedule that we can set it up and we can deploy whatever node, because it abstracts all the cluster as a single node. And then the other part is the network topologies that we want to test on. So for now, I've done the experiments to say how to understand how Liku works internally. So when we began just with 3 clusters, and we noticed that when you do the offloading, there's no way to say, okay, the second and the third can have like a direct tunnel. So the communication happens through the central or the home cluster that you say on your presentations. And I was thinking if there is a possibility to have like, let's say, a manual way to do that service reflection, to say, okay, this pod, I want this service to be reflected on these clusters, because there's no other way for now. You just need to use that offloading system to have this service reflection. So, and I'm very interested about the, like, what you have mentioned about the progress and the improvements, because we see it as a very interesting tool to experiment with. So I don't know if you have some answers, but I'll be interested to hear from you.
Yeah, so thanks for the comment. I have a partial answer, and I will invite you to set up a dedicated call with the team and ask them the precise answers. But yeah, direct connectivity between clusters, let's say A, B, and C, so B and C directly, is not currently supported. We were working on that in the last month to realize that it requires a huge amount of work in order to be supported. So the point is there anybody trying to use this in a real use case in production? And the answer so far is no. So, it was a big surprise for me, because I come from the university world and say, wow, it doesn't work this way. All the communication that goes to the central cluster. We have to enable direct connectivity, but actually the market probably is not ready yet. So having limited resources in terms of engineers working on this project, we have to do some choices. And right now, the direct connectivity is not the top priority. But okay, open to change our idea whether there are companies that are willing to go that way. Okay.
Okay. It would be interesting to discuss that, because we are very interested to to handle some arbitrary topologies, etc., in the current projects. Okay, let's keep on contact. If you can provide us a way to contact the team, that would be cool.
Thank you.
And perhaps having some suggestion, even a workaround, perhaps we can do it, even if there are some workarounds. We will also be interested, even if it's not clean or through like a command line where we can hack into the system. That would be also interesting if it's possible. Thank you.
Thanks.
I think it's my turn now, according to what Ferran wrote.
Yes,
thank you very much for the. Thank you, Ferran. Yes. Yeah, I'll try to be brief then. Thank you very much for the talk. Very interesting. I have a couple of questions. For probably easier question, I think. The first one is about whether the resources that are advertised or peered, as you said, by the, let's say, the foreign clusters in your example, are reserved for the I mean to the home cluster in the example, and if other services that try to access the foreign cluster directly from the foreign cluster can collide, or if there's a conflicting issues here. And the second question is about you were mentioning that the latency is in terms of deployment is linear with the number of levels that you have. And so I was wondering if you could have multiple level and build a kind of hierarchy of cluster up to a huge big node at the top, and whether this would imply after that. Thank you.
Okay. So let's start from the second. We never try to have more than 2 levels. In theory, it works, but we never tried. With respect to the first question, sorry, I was taking notes. I don't remember exactly. The question was
was about the fact that whether if you have, in your example, you had, yeah, exactly.
Reserve resources. Okay, so resources are reserved in the other cluster. So I don't remember exactly. Alessandro can tell you. So I give the floor to Alessandro. But when the other cluster gives you some resources, like I can give you 100 CPUs, you are not allowed to use more than 100. So this is definitely checked, and it has been introduced in the last few months in production. For the rest, Alessandro.
Yeah, no, at the moment there is not a reservation, a stronger reservation of resources, in the sense, at the moment by default, Lico shares about the 19% of resources, if I remember correctly, to all the remote classes. So it means that if you have 100 CPUs, the remote cluster by default will have the remote virtual node will have 90 CPUs. And this is true for each remote cluster. Obviously, this is completely customizable, so you can change the percentage, and we also have the possibility to insert a plugin in this resource sharing mechanism. So we have a gRPC API that you can implement in your external service, and you can do the logic you want. So you can share the amount you prefer basing on the remote cluster. You can reserve it separately outside of Lico, whatever you want. But by default, Lico at the moment does not do this strong reservation of resources.
Okay, thank you very much. I understand. What happens if you have a request for deployment on the home cluster, and then like that in your example, for instance, ask for 90 CPUs, and then you have at the same time, or more or less at the same time, the same request from the foreign cluster, not a user of Lico, but a regular user of the same cluster that ask for the same 90 or even 100 CPUs. The first that arrive wins, or there are some policy that would regulate this?
The first that arrive wins, but I say you that the resources are continuously updated. So if you apply at the same time, okay, you have a race condition concurrency problem. But during the time, if the remote cluster has fewer resources because some applications are scheduled on the remote cluster or with Lico or separately with a direct apply to this cluster. Also, the shared resources will be updated accordingly to these changes. So your virtual node, you will see your virtual node to be bigger and smaller depending on which resources are consumed by the remote cluster.
Okay, I see. Thank you. So it's a kind of a best effort situation.
Yeah, exactly.
Yeah. Okay. Thank you. Thank you very much.
Thank you.
Okay, so my turn.
We have to only. Yes, exactly. I think it's the last questions.
Okay, thank you, Ferran. So one is quite fast, simple. So if you measure how many resources are used by Lico to run, both on the entry point and the paired cluster. So let's say, how heavy is it in terms of resources is the first question. Second question is, about accounting. So how difficult is it to implement accounting in Lico? So to measure how many resources are used by different user, deploying different application in each cluster. So do you have a monitoring system that can measure all the resources how many resources are used in each cluster and for what and for whom? That's it.
Okay, thanks for the question. So let's start with the resources that we use. Actually, the resources that we use are really a few, really few. So let's start from this. So the memory. So the memory that we require for Lico to run is on the order of, between 100 and 200 megabytes of RAM. So depending on if you are the home cluster or you are the foreign, so the remote cluster, but that's the order of magnitude. Consider that the lightweight Kubernetes that we have, more or less, which is K3S, requires 1 gig of RAM to work. So K3S requires 1 gig, you had 100, 200 megabyte more. Okay, that's the order of magnitude. Definitely, it doesn't go on an embedded device. Okay, that's clear. In terms of CPU, it's almost zero. So if Lico doesn't do anything, it does almost zero. And the same for the network consumption. There is a keep alive between cluster, but it's order of 100 of bits per second. So, I mean, who cares? Lico consumes more when there is something to do. So it's interesting here when you look at this green band here. The green band, you can see on the bottom, is the time in which we offloaded 1K pods. So we started 1,000 new pods. And those 1,000 new pods have been scheduled on the remote cluster. And of course, Lico comes into play. So we consume more bandwidth, of course, network bandwidth, because we have to align the states. But the value is, in this case, 4 megabit per second. So it's not that huge. We consume more RAM, of course, because we have to create more resources and information and keep them running in the cluster. And of course, we consume more CPU. But to my understanding, and this is an opinion, the resources that we are consuming are really negligible. 0.5% of the CPU cores that we had. So it's almost nothing, okay? And the memory, maybe the memory is something more, but simply because when you run more pods, you have to create some more information anyway. So if you run 1,000 pod in Kubernetes vanilla, you consume more memory. That's clear, okay? So, in the end, my feeling is that the consumption that we have is pretty low. But again, this is an opinion, so you can have a different opinion. By the way, this time is basically the time required by Kubernetes to schedule those 1,000 pods. So if you try to schedule those pods on your home cluster, it doesn't take so little less. Okay, so it takes almost the same time because Kubernetes try to do things one after the other and so on. So even this time that we are measuring here is not that different from vanilla Kubernetes. So, our feeling is that you can hardly see the difference in terms of resource consumption. Personal opinion, of course. I don't know if this answers.
Yes, thank you. And what about monitoring for accounting?
Okay, monitor for accounting. I leave Alessandro for a better answer, but you know, in the end, you still have a vanilla Kubernetes, almost a vanilla Kubernetes. So if you want to run whatever tool that gives you those numbers in a vanilla Kubernetes cluster, that tool should work also with Liquid enabled. So if you run on the main cluster can see also the other cluster, and that's it. You cannot see individual servers, individual nodes, but all the rest is visible to you. So I don't expect differences here.
And
So
also
you
in
can use
the,
cost or whatever.
also in the remote cluster, you can check which cluster the pods are related to, because we add a label on each offloaded pod to know the origin cluster. So you can also check, for example, if you have a monitoring tool in the remote cluster, for example, Grafana, Prometheus, something like that. You can also use this label to understand the origin of these running pods, if the question was in the remote cluster.
Okay, thanks.
Okay, I think Tariq, if you want, you can send him an email, or maybe Fulvio wants to answer right away. But I think we already passed the time, and let's decide about Fulvio. He has the time to answer.
The question from Tariq was if the tool can help us to expose arbitrary services on the opposite cluster. Definitely yes. This is something that we use massively in our data spaces projects. So we have two clusters. Pods are running on one side, but they are exposing their services also to the other side without moving pods. Perfect. And this works smoothly. This is something that we really need in order to control better and have the ownership of the pods. So pods are working on where I want on my cluster, but allow remote access from the other clusters. So yes, definitely.
Okay, if there are no more questions, I think I will thanks to you, Fulvio, and also Alessandro, for giving us that nice demo and also the talk. And it was a pleasure to listen to you about all your great work that you have been doing for liquid computing. And I think more of the people that attend the webinar will send you a couple of emails. I'm sorry if there are so much work. Thank you very much for your time, Fulvio and Alessandro.
And how we
thank you
can
for
contact
inviting
you,
us.
please? How can we contact the team? What are the ways to contact the LICO team?
For a question about the code things, it's Slack. But I will send this presentation to Ferran, so you have all our contacts directly. So you can also.
If you go on our GitHub page, our GitHub repository, there is also the link for Slack and everything.
Okay. Thank you.
Everything you want.
Okay. Thank you very much. Thank you very much.
Thank you very much.
Thank you.
Have a nice day. Bye bye.
Bye bye.
Bye bye.